All right, so what we're going to be doing here in this workshop is I'm going to be actually teaching you a lot of the basic, intermediate, and some advanced physics and mathematics so that you can actually build your own systems. So it's not just going to be a regular DIY where they just like, hey, this is how you do things, blah, blah, blah. I've actually got graph paper here. I've got paper here. I've got plenty of pens. There's no excuse. There's more than enough for everybody. And we're going to actually sit down and we're going to design something. And I'm going to teach you what it's like to be an engineer and making your own whatever you decided to build, because today is Tuesday. We build things on a regular basis where I'm at. I'm with the board of directors for International Institute of Research and Development, as well as several other organizations that I sit as a member of, or as a board of directors of. And I also own several companies, and we specialize primarily in research and development of probably some of the craziest technology that unfortunately most people will never get to hear about, because it's for DoD and other organizations like that. But I've built a lot of crazy things in my day, and NSA? I've got a lot. Huh? NSA? Yeah. I actually helped build Fort Meade and tore down Sky 7, so that was their last home. It's not really. They're like all over the place nowadays, especially in Australia, which I still don't understand. There's something about kangaroos and spiders that want to kill you. But yeah, so one of the things that I will say before we get too heavily into this is please hold your questions for a little while, and that's so that I can get you up to speed to the point where you'll need to be, because I'm not assuming that anybody knows anything about anything ever. For advanced people, this might be a little boring for a little while. For some people, though, it'll help you get to the point where everybody's on the same page or close enough to it to where you can function in the meat and potatoes, as I like to call it. So we're going to jump straight on into the content. This is a breakdown of what volts are. We're going to cover volts, amps, and watts. They're the three core pieces to anything electrical of any kind or electronic. Without those three core aspects, everything just blows up the second you plug it in. Another thing that you have to keep in mind is SI units and non-standard, which is very prominent these days, where people just kind of shot from the hip, made a couple of things, and well, as engineers, we just adopted it because we liked it and it made our lives a lot easier. But going on in, jumping into this, a volt is a derived unit of electric potential. So when you're looking at a volt, it's not so much a V on a battery or something really sparkly that you see coming out of a taser. It's more so of a concept of pressure. And that'll make a lot more sense in a little bit once we start getting into current for amperage. And wattage, which most people in here, if you've got a computer, are familiar with, is wattage, which your power supplies leverage. But it's electromotive force, and the easiest way to experience voltage in a safe manner, which we're going to see some other ways of experiencing voltage here in a minute, is take a balloon, rub it on the floor, and then hold it over your hair. That tingling feeling that you feel, that's a low voltage pressure. And that's what most people have experienced a lot in voltage. And when you touch something, that's voltage discharge. So that's you actually grounding out, and you end up actually getting electrocuted. So everyone has been electrocuted at least once, hopefully. Pretty great. So the formulas are very important in this presentation, which I'll be sharing with everybody. The formulas are in here, both the basic, the advanced, and the extremely advanced ones. We start looking at leveraging alternating currents on one-phase and three-phase. US uses one-phase and three-phase for some weird reason, and burns like 70% of the power they produce just trying to get power to houses, whereas in the rest of the world has common sense and leverages three-phase. But do keep that in mind when you're working with alternating current, because it does impact how your formulas are calculated. But going on to the next one, this will be our first video. I like this video, it's great. So this is going to help you break down and understand what voltage is and why voltage is. So you've got two tasers, both are at 25 watts at 9 milliamps with 200,000 volts. The other has 7 watts, 1 milliamp, and 1 million volts. You decide to let your friends tase you with a taser. Which taser do you choose?
The latest.
The latest? So the first one or the second one?
The second one.
Why?
Because it's not the volts that's going to kill you, it's the amperes
that is correct. A high number voltage doesn't really mean much. It's a lot of pressure, but if I blow on you with a lot of pressure for a microsecond, you're not even going to move. You're not going to feel anything. It's the current that kills you. And with 1 milliamp, you're literally not going to feel it. You're not going to feel anything. So I openly welcome someone to tase me with a 1,000,000-volt, 1 milliamp taser, especially if I get free beer out of it. This 25-volt one, white one with the 9 milliamps, that'll put you on the floor for like a good 20 minutes. And we'll come back to that video because it's just the best video. So getting into watts, a watt is a unit of power. So when you hear unit of power, you think electricity. Well, that's not necessarily the case. There are multiple ways to measure and calculate power. It's based on the concept of application. Power for one thing could be electricity. Power for another could be lifting or moving capacity. So it really depends on your application. For ours, we're going to leverage the International System of Units, which is the SI units. I don't know why they did it this way. I think IS unit would make more sense because International System of Units, but they did SI units instead. So it derives it as a unit of 1 joule per second. So a joule is a measurement of energy, which again, just like the other form of power, has multiple applications based on what you're leveraging it for. In our instance, it will be stored capacitance of energy for electrical application, which will have a relative application to almost everybody in this room. If you've ever gone looking for a mobile charger, for instance, you've noticed that it's an mAh, which is milliamp hours, and joules, which is when marketing teams just hate everyone and decide, hey, it's a big number, let's use joules instead, because the calculation back to milliamp hours is a nightmare, which we'll cover later. And watts are commonly called power. It's named after James Watts. He's done quite a few things, dead now, to include horsepower. And watts are leveraged for the measurement of power in pretty much everything we use, laptops, cell phones, batteries, car batteries. It leverages watts, but batteries also leverage amperage hours, but we'll get on that later. So these are the formulas. Watts equals 1 volts times amperage. Like I said, this is extremely significant based on whether you're looking at alternating or direct current, because alternating current has 1 phase and 3 phase, and it impacts your formulas for calculation. This is a demonstration of the confusing nature of application. Like I said, 1 watt equals 1 joule a second, Newton meters a second, kilograms meters squared over a second cube. It's really depends on the application and purpose. And then we get into another one, which is voltage over ohms, which is resistance. So if you've got a current that's drawing off of something, or you have to, say for instance, take a 9-volt battery and make it work on a 1-volt circuit, you'd want to leverage something that generates resistance, which we'll also cover later, to lower the voltage so you don't blow something up. Computer electronics are a perfect instance of this. If you open up your system and look at your motherboard, it's got resistors all over it, because some components are incredibly electrically sensitive, which is why they tell you to ground yourself out before you touch anything. Because even the slightest shock from something as simple as static electricity can fry your board permanently, which are extremely expensive. So, getting into watts and really breaking this down, you have 16 Deca 12-volt 100-amp DeepCycle batteries. DeepCycle batteries are usually leveraged in systems like car stereos, motorboats. If you've got some kind of entertainment system on those, they're leveraged in marine batteries, is what they're also called. Leveraged, like I said, a lot of times in ships. They're leveraged in anything that's mobile, that's used to keep something on or active for a long period of time, like food trucks. They leverage DeepCycle batteries. And so you've got the DeepCycle batteries. They're brand new. They were just given to you as a donation to your hackerspace. And you want to run a rack of Dell R10 servers with 1,000-watt redundant power supplies. How many servers can you run?
What power supply? 192 servers.
That's 192 servers, yeah. Answer's right there. But yeah, so the answer's 192 servers. So what you do is you calculate out the wattage to get by getting the amperage and the voltage. So you multiply these together, then you add it based on the number of batteries, 16 batteries times 12,000 watts for 192 watts, and then the 1,000 watts for the servers for 192 servers.
I've got a question.
Yes.
So what is 1,000 AMP?
Amps?
Yeah.
It's amps.
Yeah.
So that's the amount of amperage.
What is hours for this?
So
Capacity.
okay.
Capacity
So
is not.
yes. So amps is how much current it can generate.
Yeah.
Ampere hours is how long it can generate that amperage of 1,000 amps.
But what is the capacity?
So the capacity is measured in ampere hours in batteries, especially deep cycle batteries like these.
Yeah, but what is the capacity of deep cycle battery of 1,000 amp?
Well, it depends on the battery. So just because the battery can generate 1,000 amps doesn't mean that each battery is equal. Like a Duracell versus a cheap battery, it may have a milliamp hours of 1,700 versus
so
2,800.
the answer tells us how many servers, but not how much time.
Correct.
Okay, good.
Correct. And that's where the ampere hours would come into play, because that would tell you how long it will last for. Other things that come into play is the Picard law, which we'll cover later, but that directly impacts certain types of batteries substantially. They actually lose a massive amount of capacity because of the amount of draw that they're faced with. The higher the draw, the faster those batteries die, and it does not go to a 1-to-1 ratio. But yes. We're going to cover several other topics like series and parallel together, which is also very important, especially if you're going to try to build something that lasts or runs for a long time. So getting into ampere, most people know it as an amp. The technical term is ampere, named after the guy who technically discovered it, Mr. Ampere. It's a unit of electrical current equal to the flow of 1 coulomb per second. Ampere is commonly measured in amps and is called current. So a lot of people switch around amps and current. It's the exact same thing. Current's measured in I. I don't know why they keep making these things more complicated than they need to be, but yes. So it's technically a calculation of the electron flow in an electrical conductor. Batteries in mobile forms leverage ampere hours, farads, or milliampere hours. Mobile devices are going to most commonly be measured in milliampere hours, which is M capital A, lowercase h. And then amp hours for marine cycle batteries, which would be capital A, lowercase h. Farads are for capacitors, and the capacitance ratio, which I didn't include in this because it would be going way deeper than we need to. If you're leveraging any kind of capacitor inside your build, talk to me, because you might get yourself killed. Capacitors are incredibly dangerous, so please don't play with those or buy those until you're a lot more comfortable with them, because they will absolutely kill you. I've had several friends get hurt really badly by capacitors, and I've almost been killed twice. So they're very dangerous. So 1 ampere of current represents 1 coulomb of electrical charge, which is actually broken down into charge carriers, which is 6.24 times 10 to the 18th power, moving past a very specific point in 1 second. So if I run this Coke across it, and that right there is a wire, it's measured at the point where my wallet is. So the second it runs over my wallet, in that 1 second, it counts in 1 second how many electrons it measures. That's the calculated number of electrons. And then electrons themselves carry a specific potential charge of 1.602 e to the negative 19 power coulombs of charge. So this is the number of charge carriers, electrons. This is the charge of the electron itself. Those two combined together tells you the actual amount of energy available at that one moment. And then 1 amp flowing for 1 second on a wire would use 1 coulomb of charge. So physicists generally consider when you have a wire with a completed circuit, a point to where things move from relatively positive to relatively negative. And that's how the circuit works and why it works. Why that is, that's incredibly high-level physics stuff that's beyond me. Consult a local physicist or a college if you want to know why. I don't know why, and I honestly never bothered to find out. Some things are just too complicated and go beyond a need for understanding. But getting into that, we're going to jump in. So you got 20 servers running with 20 amp circuit, and the circuit breaker is continually flipping. If you're ever working in data centers, this is a constant frustration, or if you have your own private lab at the house. And the servers are causing you to shut down unexpectedly and unintentionally, which normally causes corruption issues and blows up your lab and ruins your day and probably your weekend. So the servers are Dell R610s, which are a standard lab server that most people buy, low cost, running a 750 watt power supplies, running on 110 volt single phase residential power, because in the US it's residential single phase. And they're constantly running at 100% power load. Now that is generally not the standard. Most servers run between 15 and 65% power load, but we're going to say 100% power load to not make things more confusing or complicated for you. So how many 20 amp circuits do you need, and how many servers need to be on each circuit to allow for a 20% power surge? The reason why you allow for a 20% power surge is when your devices spin up on a regular circuit, they're going to pull their full potential power for a brief moment and then spin down to their standard usage, which is called average load. And so that's why you could have a system where total calculated amps is like 70 amps on a 20 amp circuit and everything works just fine. Normally, as long as you don't cut them all on at the exact same time, which is why you were supposed to give each of them a few moments to spin back down so they stop consuming power. But yeah. So how many servers can we put on it?
There's solutions there.
I know. But yeah, so we could put roughly 2.346 or 2, because you're not going to have a fraction of a server unless you're running Raspberry Pis on the system, and that's because of the load acceptability and the amperages available per circuit. Now the reason why you do this is certain servers or certain systems that you build out, especially something leveraging pixie booting, if you blow away your servers, say for instance you're running a diskless model and your systems die, they all have to pixie boot back up. If they're all on the same circuit, when that circuit flips again, they're going to pull load again at the same time, and that's going to kill your circuit again and again and again. Now, that's also assuming that you've got all of them running at 100% ratio, which is hopefully never the case, because you're going to kill them far quicker. Running electronics at 100% capacity or even above 80% is going to drastically degrade their lifespan in a very short period of time. Now, this is going to be a brief covering of alternating current and direct current. So alternating current reverses directions many times a second, which is frequency, regular intervals typically used in power supplies. All of your power supplies operate normally in a frequency of 50 to 60 hertz, which is roughly 1 every second. Now, you'll also notice on there you see a plus or minus percentage, normally plus or minus 5%, and that's because power isn't always stable. It's never stable. If you've got perfect power, you've got power scrubbers on your system, and it's running through a crazily expensive system to clean your power to make it completely stable. Pretty much the only place that's guaranteed to have that every time is a hospital. Everywhere else, they're just like, throw it the ups, hope it doesn't blow anything up. And then direct current, which is what most people are used to using on a regular basis. Direct current flows in one direction only, and it's almost always in batteries. I've never seen anything else leveraging direct current other than a battery usage, unless they're doing something incredibly weird. There's no reason to convert AC to DC for something that's not battery related. Which your cars, they do use DC, I guess, but that's also pulling out your batteries, so I don't think that counts. But yeah. So ampere hours. So this is the one that's very important. So this is the one that you can check on your car battery and find out how long your car battery is supposed to last. As well as your mobile battery devices. So say for instance you want to know, does Duracell or Rayovac the better battery? Well, flip it over and look at the ampere hours for the power provided, and then you can calculate which one's actually better by calculating it 2 joules to find out the overall power capacitance of the batteries side-by-side comparison. But it's easier to use milliamp hours, which is why most people recommend milliamp hours. I recommend milliamp hours, but there are some cases where joules is useful. So if you've got multiple batteries of different types of different voltages and you want to know, well, I've only got 3 different types of batteries to use and I need to get a certain amount of energy available, I can leverage these 3, use a transformer to spin it up to one specific current, and then the batteries are just going to die really fast, but I got to have the power for some reason that I can't explain. But that's one instance where you would use joules instead, but generally it's not common. But yeah. So ampere hours is leveraging an amp hour. So you multiply the amp by seconds. 3,600 seconds is 1 hour, and that gives you your amp hours. So it's effectively just multiplying your amps times 3,600. So it's pretty simple, and it's calculated to 3,600 coulombs. But yeah, so understanding amp hours. So this one is actually going to help people a lot. So if you've ever got a battery and you're really frustrated that your laptop just dies all the time. I had this problem for years with HP laptops where it would just die and die and die. I could get like 30 minutes of usage before it just kills itself. It's really annoying. And so you've got a laptop, it's drawing 500 milliamps while in use. You want it to last for a day. What is the capacitance that you need for your battery in amp hours? Which is, it's half an amp times 24 hours, which is 12 amp hours. So that puts you well within the range of a car battery or a really nice lithium-ion battery, depending. So your average lithium-ion battery, strip this long, about that wide, you're going to get 6 to 8 milliamp hours. Amp hours out of that, and you could easily just push it to where it's running better. So you could replace it, upgrade it, lithium polymer battery. Really depends. Or you could just jerry rig your laptop, cut out the bottom face plate, remold it on with some electrical modifications there with some putty, and then ground it out, and then kind of like MacGyver on two batteries at the same time, put them in series and parallel and connect them together. So yeah, I would not recommend that. It definitely voids your warranty. But it does work. It does work. So milliamp hours, this is where you're really going to see most of your stuff, your cell phone, your watches, medical devices. They go off of milliamp hours simply because it's mobile, and messing around between going 2 and 4, they don't want you to mess with the math. And plus milliamp hours, it looks bigger on the screen. You got like 12 amp hours. You're just like, what? Like 4600 sounds way better. So they're both usually described to describe capacitance of a battery and how long it will run before it needs recharging. Now, what that's going to pull us into is what's called a charge cycle. So this is what you're really going to appreciate and understand why your devices keep dying so quickly. It's actually because your charge cycles, the way you treat your charge cycles, it's actually killing your battery. And depending on how well your laptop or whatever device it is was designed, you might be killing your device a whole lot faster than it was meant to die. So we'll cover that in a minute though. But yeah, so jumping into the milliamp hours, especially for drones, you'll see Arduino. I openly laugh at that because in the US we all call it Arduino. I don't know why, but yeah, we just like add like 4 extra E's in there. So make fun of my friends. So you got 6 propellers, an Arduino controller, 2 Raspberry Pis, each with a draw of 500 milliamps. How many milliamp hours does the battery need to provide adequate power for the usage at 100% load for 1 hour? So you're right now at this point applying it to the application of, I want to put a drone in the sky with 6 propellers with a remote controller and 2 Raspberry Pis because I'm capturing Wi-Fi off of this skyscraper I'm pen testing, and I'm stealing your data by mining you floor by floor. I've actually done this on a pen test. It's really fun. You should definitely try this sometime. Well, you should try it legally sometime. Yeah. So this is how you calculate it out. You literally just add them all together. So 6, 1, and 2, so 9 for the milliamp hours, so 4,500 for the time of 3,600 seconds. And it gives you 16.2 milliamp seconds. And then you split it by coulombs, and you've got 4,500 milliamp hours. So this could actually, you can go take one of those just regular chargers for extra battery packs that you've got at like your average cell phone store. Go in, pop it open, and then you've got 4,500 milliamp hours, just so you guys know when you're going to go buy your batteries. So for like 15 bucks, you've got a local lithium battery that's like hardcore. But yeah, just don't stab the lithium battery. We have a problem with that in the US. Yeah, it's actually warning labels for it now. So joules is derived as energy for the International System of Units. Joules is a correct measurement of energy. It is not the ideal measurement of energy, even though it is the standard measurement of energy. The issue with measuring everything in joules is say for instance you've got a 9-volt battery and he's got a AA battery, and your battery is just crap and his battery is just awesome, and you've got the same amount of joules. Well, the problem is I don't know the difference in joules, but I know that I need a 9-volt battery. But if all you're telling me is joules and joules, I don't know which battery I need. So I either buy the wrong battery or I just happen to get it right. So that's the reason why you want to use milliamp hours, and you want to always divulge the proper information, which marketing companies are infamous for. They want to use joules because it's just a stupid long number. It's almost always in the millions, and it looks great on paper, but it always upsets your customers. So if you're a hardware vendor, never put anything in joules, always milliamp hours or amp hours. But yeah, so it's equal to the energy transferred or work done. So it's the conducting of work on an object with a force of 1 Newton and a direction of motion through the distance of 1 meter. So that's a Newton meter, or NXM. So I used NXM instead of N.M because it's Windows and it doesn't have all the units it should for some odd reason, to include the ohm symbol, which was really weird. And it's also the energy dissipated as heat within an electronic current of 1 ampere passes in the resistance of 1 ohm for 1 second. Now, one of the things that you're going to have to keep in mind, electronics get hot. And when things get hot, things cook. Lithium cooks. And when it cooks, it explodes. So, drones blowing up in midair, not cool, man. Not cool. Hackerspace meetups, I don't do drone builds anymore because I've had too many pieces of plastic rain down on me. Like, I like the song Rain Man, but I mean, come on. So, alright, so understanding joules. So a battery vendor lets the marketing team decide what format to display the battery capacitance in, and because joules is a larger number, they said use joules. This is a very common problem. You will see this. So you're looking for a new battery for your mad scientist project, and you think you like this battery because it looks cool. Batteries that use joules almost always look amazing. It's the telltale sign that they suck. I promise. So you're looking at this new battery and it looks awesome, and you think you want it because it looks cool, and you got another battery at the same price for 45,000 milliamp hours. What battery do you buy? So, you want to buy the battery based on the calculation. So this is why, again, looking at joules is a nightmare. This is the process you have to go through just to translate it back to the milliamp hours. So you've got like 6 calculations right there to do, which is why it's really frustrating. And when you're going through eBay, for instance, and you're looking at 5 batteries at a time, this is the math you have to do to get each battery's MAH, to get them all to the same standard, so you know which battery you want to buy, which is why it's really annoying. And when you're buying your batteries, you want to do a price per performance, so PPO, of cost to milliamp hours. And so the one with the higher number is the one you want to buy.
So why and who use joules?
Pretty much the only reason to use joules is, for instance, if you've got multiple sources of power. So you've got multiple redundant battery systems with one system using auxiliary power with a power transfer unit. So all the power is pouring into one location. And you've got multiple types of batteries for each one of those. They've got dedicated power you're supposed to use for that purpose. But say, for instance, your primary power dies, and the system's got a built-in safety mechanism that automatically translates that to where all your power is transferring away from all your auxiliary services directly into where your main power would feed into, so that X safety something can happen, because that's always the reason why. It's a safety feature. For some reason, everybody's all about safety. Yes?
I have a question. Where did 9 volts came from?
So 9 volts.
Yeah.
Did I forget to add a calculation in there?
Yeah.
Oh, my bad. I was supposed to say this was a 9 volts. Sorry, that's on me.
Because sometimes the battery producers, they do the same. They do not say how many volts.
Yeah.
They
See,
just
this is what I was talking about,
amperes.
having missing information. I messed up and left something out.
And they confuse because you don't know how many volts.
Exactly, and you need to know how many volts, because you're missing. If you're missing more than one component for the calculations, you won't be able to complete the math. Which is why you have to have all the information. Which is here a perfect reason why. Well, how do you got 9 volts? Well, that's a great question, because I knew what I was looking for and I forgot to say. But yes, so this is how you would complete the math. But yeah, this is based on 9 volt batteries is what I was looking at when I was doing this calculation. I was comparing Ravax with Duracell 9 volts. But yes, so this is what you would be looking at, and yeah, it comes down to 4,600 milliamp hours, which you're going to see this number a lot in that ballpark. 4,500 is a really common place to be. If you start seeing something above that, let me know, because that's a nice battery, especially if it's cheap. So this is where we're getting into charge cycles. So a charge cycle is really simple. It's just the concept of you're using a device, you've got this device, you get it for the very first time, no one's ever touched it, never used it, never even turned it on, which is never the case. The factory turns it on at least once to test it. So you've got this device in, and you're using it, and you're using it, and you're using it, and you start to notice it's not lasting as long. It's you'll have like, yeah, I can listen to my music for like 4 hours, and like next month it's like I can get like 3.5, and then 3, and then like 8 months later you're buying a new cell phone because it's dying every like 35 minutes. Well, that's because of the charge cycle and the expected life expectancy of the device. So batteries are listed by charge cycles if they're rechargeable, and they have an expected amount of charge cycles that they're expected to survive on. Now, good engineers and great engineers can be picked out simply by one practice, which is I calculate the amount of power minimally needed in order for the device to perform, and then I add an additional 20% to that. And what that allows me to do as an engineer is to drastically extend the lifespan of the battery, not just by 20%, but by an additional sum, because when you deplete a battery fully, you're actually damaging the battery. So you should never run your devices all the way down to 0. That's a really great way to kill it. I know a lot of people have this thing about cell reset. That's complete crap. Lithium doesn't just randomly forget that it's a lithium battery. It's a lithium battery, and it will always recharge back to what its expected capacitance is for the battery.
Even if I do it once in a half year?
Yeah, once it's not going to hurt it, but if you're like constantly just like, I'm going to listen to myself until it just dies because I have nothing else to do on the train and just keep killing it and killing it and killing it, you're actually killing it, and you're going to have to buy a new phone or a new battery, which these days they're almost the same price. At least for mine, anyways. I have a tactical phone, so it's weird. But yeah, so this is going into what I just iterated on. So this is the simplest way to calculate that for your devices, especially with drones, because you're going to run them for as long as possible to get those great shots, to get those great views. You really want to take this into consideration. Yes, you will spend a little bit more, but I promise you, the first time you have to replace that battery pack, you're going to regret not doing this, because the cost of replacing the battery cell entirely as compared to just buying a slightly better one is just too much money. I made a big mistake and had to replace like 50. It was not a happy day. So you've got your system here, you're running it. You got the calculator? Yeah. Okay, so this is taking that same calculation that we just did, and that's including the proper engineering into it. So the battery capacitance that we need is 5,400. So obviously 4,500, a normal one, so that's exceeded by 5,400. So now we need 2 batteries, which leads us into series and parallel, which we'll cover in a moment. And that's why series and parallel are important. And understanding the difference is also important, because one adds more time, one adds more voltage. And as I said before, adding too much voltage, you blow stuff up. So using the right one, the right time, the right way, very important. It's also why if you see a lot of child's toys, they'll use multiple AA's instead of a 9-volt battery. So, yeah. But yeah, so rate of discharge is a term for the rate of load, also known as draw. So people will interchange those, load or draw. It's pretty much the exact same thing. And it's placed upon a source of energy, whether it's an AC or a power supply or a DC. So it's literally just, what am I pulling power from? I'm putting my draw on that. It's the same reason why if you watch a Stirling engine on a desk, it spins really crazy fast, like 15,000 RPMs, until you add literally any draw to it whatsoever, like a 1 watt LED, and it just slows to a crawl. And that's because of the draw. So the rate of discharge is impacted by a variety of factors, to include number of devices, sources of power, the Purcart effect, and ambient operating temperature. This is something so many novice engineers forget, is the ambient operating temperature. So ambient operating temperature will drastically impact a variety of things, how long your electronics actually survive for, because heat damages your device over time and it degrades it. And as you degrade it, you can only degrade it so much before it just kills something. It impacts your battery life, so if you're talking on your phone and you feel your phone getting really hot, hang up the phone because you're killing your battery. It's dying. So it's very bad because you're adding more heat and you can literally have it blow up in your hand. That actually happened to the Note. Which Note was that? Several? Yeah. That's happened to several devices lately just because of bad thermodynamics of the device. Because they want to go, fanless. Okay.
What is Purcart effect?
The Purcart effect, we're going to cover that in a moment. But effectively what this is different batteries have different levels of draw load that they can handle. And it's like giving a 5-year-old 500 pounds to carry and giving an adult 500 pounds to carry. They can both carry it the same, but you're going to crush the child in the process. And so it's the same process and same concept. Is if you're a bodybuilder and I hand you 50 pounds and you hand me 50 pounds, I'm just going to put it down because you're crazy. The bodybuilder will laugh, start juggling his and mine. He just doesn't care. And that's pretty much the implied effect for cars. But in terms, it's a drastic decrease of some batteries' chemical production of ampere hours if they are rapidly discharged. So say, for instance, you give me the 50-pound weight and you make me carry it by some act of God or miracle or bribery with food or beer. If I'm carrying this thing, it's incredibly heavy to me. So I'm going to get tired out very, very quickly. I'm not going to perform normally. Whereas in this guy, he's just jacked. So he's going to be like, whatever. Just like walk away with it like he doesn't even care. Now what that does to a battery is certain batteries have a very substantial impact to you. Some batteries have a very minimal impact to you. The batteries that we currently use today are the ones that have the minimal impact. And that's why a lot of people got away from these kinds of batteries. The alkalines, the carbon zincs, the zinc air, the lead acid. And it's just because our devices are drawing more and more power on a more and more regular rate, ever increasing every day with more updates, more software, more applications. It's pulling more and more and more from the device. And the issue is the battery's chemistry can't handle it. It's forcing it to react too often, and it's just wiping it out to like a 50 to 70% decrease in performance. We're talking like a landslide, walked in, fired half the IT staff, just bottomed out, like it was a bad day. Now the performance is technically noticeable in these types of batteries, but it's not relevant. You're talking like a couple of points. It just, doesn't matter. Especially if you engineered things properly, which is why, again, that 20% is so relevant and important. Now we're going to get into series and parallel and understanding these because it's very important. So this is negative to positive to negative to positive to negative to positive to negative to positive. So in one row, it's a straight shot in a series with 3.6 volts at 3,400 milliamps. And what this does is in a series, you add the voltage together. So you're increasing the voltage with every additional item you add. So every additional cell adds more voltage. And yes, you can put in better batteries and worse batteries. I can swap out this 3.6 with a 9 volt. However, that causes a substantial amount of issues for these batteries because they don't operate on the same level. The same can be said if you have a bad battery. That's why they tell you don't mix batteries. Because if these are like a day old, a day old, a year old, a day old, this battery gives first, realistically. What ends up happening is the draw on these other batteries is increased to countercompensate because this battery isn't performing optimally. And what ends up happening is you kill these 3 batteries faster because of that, which is why they tell you don't mix the batteries, also because, you know, the lead acid all over your everything. Yeah, I've lost quite a few fun toys because of that. And it's the same milliamp hours. It doesn't impact your milliamp hours. That's series. Now, you've got 10 9-volt batteries in a series, 40,000 milliamp hours and 20 milliamps and 20 milliamp hours. How many volts do you have? It's simple. It's 9 times 10. It's 90.
Yep.
So it's straightforward. Now, getting into parallel. Parallel is totally different. This is all negative at the bottom. That's all positive at the top. With one connection for positive, one connection for negative, and that's how you interface with that battery cell, which this is a battery cell, battery cell, battery cell, battery cell, but engineers typically just say the battery cell. And that's because, you know, if I said battery cell A through F, you know, it would get really annoying, especially if you've got 200 batteries in something. In parallel, it's the opposite. Instead of adding the volts together, you add the milliamp hours together. And then you've got 3.6 volts. Again, same issue. If you use a defective battery, it's going to damage your batteries and kill them faster. Now, what gets really fun is when you start to play with these together. So, you're going on a trip with a local security event that's 15 hours away on train. You're traveling with one guy from your local hackerspace that doesn't like cats, video games, or computers. Who likes this guy? Exactly. Nobody. How many batteries do you need to bring with you to power your Game Boy Color for the whole trip with your headphones on music with 100% volume up so you don't have to listen to them? To drown out his complaints about how hard it is to install a printer. You know that guy. Come on. Come on. Hopefully he knows I'm talking about him. He's on my damn nerves. So once you're on the train, you will not be able to change batteries because he will start complaining about personal space. And he'll go on a tirade about contact. So, what's the draw? This is something you always got to figure out. You always need to know what your draw is for your devices in a milliamp hour basis. And that's because you want an easy translation between what the draw is and what your available power source is, because trying to do this like disjointed calculation like this will drive you insane. So don't try that. It drives me insane. I don't do it anymore. It was a bad decision even trying to. So, standard AA batteries are rated between 1700 and 2800, which is a difference in quality, which is why quality is very important when you start looking at the fact that you're buying 4 to 24 batteries. Because the cost per battery, if they're the same, you're getting ripped off substantially, because that's 50% difference right there. That's why understanding why those batteries are what they are performing at is very relevant, which is why some of those batteries have that giant sticker that says last 50% longer. They're literally talking about these guys. It's like a direct shot at their competitor. And you suck. Yeah, that's what that sticker is. So, most of those batteries are rated for 2.8 hours of play per battery. Most devices use 2 to 4 batteries. The old, whoever had an old school Game Boy, I'm talking like the death brick that was like this. I was like yay long, and the case was like a lunchbox. It was like 2 pounds by nobody? No?
Yeah, we have it, but we have like the Russian version.
Okay, the Russian version. Okay. Yeah. So this thing was like a death brick. You could like throw it and just like smite somebody from existence. It was great. It was just huge. For some reason, it was also a slightly better performing device. I still haven't figured that out yet. Yeah, and it was just better. I actually pulled up the specs when I was looking at this. So I had to use accurate data from Nintendo, which turns out they started publishing it all the way up until the Game Boy Color, then just magically stopped for the Game Boy Advance. I'm guessing they had a huge performance drop, which is why they stopped. But anyway, so you do the calculations on this by getting the range. So understanding the range of performance, unless you absolutely know what the battery is, plus its tolerance for variance. So even if you've got a Rayovac battery, and you've got another Rayovac battery beside it, they are not the same. They do not have the same milliamp hours. I don't care what the vendor says. They're full of shit. They never have the same performance. Always test your batteries to verify, because they never have the same performance. So you get these, you calculate the range. You've got a range of 850 minus the 0.5, and that's because of your loss to peer card effect. Then you calculate these out based on the draw, which is your draw from your device for the load range of your device itself. Now, we calculated based off of 100% draw, so we can just drown them out in the music, but that doesn't necessarily mean the components are pulling at 100%. So you got 70 to 80, which puts you at about 1200 to 1050. You need 4 batteries, if they're good batteries, assuming they're good batteries. So this is how you calculate your batteries. Now, like I said again, be careful when installing in series and parallel, because if you get them wrong, you're going to fry and die something. I promise you. Raspberry Pis, keychains, key fobs. Yes?
They sometimes take into account that you can take the discharge battery and hit it hard, and it works sometimes after that. We do that. We did that when we were children.
I don't know. I mean, that's a Russian thing.
You should try it.
I'm going to try it now. I've never... Kinetic Energy makes... I guess it just loosened up some excess acids that were in the battery.
Batteries, just regular batteries, after they die. And if you
Yeah.
do with a hammer, a little, or a stone, and it
What,
works.
yeah, what that might be is that it's a chemical-based battery. So what might be happening is there's undissipated chemicals for non-reacted components inside the battery, and when you strike it, it loosens it up, and then it causes the chemical reaction to reactivate, effectively recharging those batteries. Don't ever recharge non-rechargeable batteries, by the way. They will explode. They will explode, like hardcore. I had to try it at least once. They most certainly explode.
Like in 1 minute, in 1 hour.
Normally in like 4 days. It takes a long time.
4 days.
Yeah, I left it plugged in
But
for like
I
4
can
days.
charge it 3 days and.
No, it doesn't actually recharge. That's the issue. Like, they just get really, really hot and then eventually cook off and explode. So, yeah. Or they just melt all over everything. Yeah. So, I mean, if you really don't like your coworkers, just like cook a bunch of batteries up and just like start throwing them. I mean, the kinetic strike might detonate one. I mean, depends how much you like or dislike your peers. But so, this is actually an event that we had a lot of fun with, and it actually works. So you're at a hackerspace meetup with friends, and you want to have a LAN party with your friends, but you're an outlet short. This happens all the time. Please bring a power strip. Like, I can't emphasize that enough. Bring a power strip. So you've got 16 Deca 12 volt, 1000 amp DeepCycle batteries available, and extra female-to-female power cables that were donated to you to the hackerspace recently. The batteries are brand new, so we're assuming completely brand new batteries. In order to make the power available to the 3 other members, everyone agrees to limit the power usage to 1,000 watts per device. Your computer uses 350 watts baseline, so your motherboard, basic NIC, hard drive, without a graphic card, and each graphics card uses 280 watts each. You've got 3 graphics cards and SLI because you want to win, and you came to play, you came to party. How many cards do you need to remove in order to play? How many batteries does each person need? So let's walk through this. Yeah, you don't have the answer this time. Gotcha. Yeah, so how do we solve this? Any ideas? We're a hackerspace, we got to solve it. Come on, I'll play.
First, I got a question.
Go
Why
for it.
female to female and not female to male?
So, a female to female, you have to cut one of the ends off. So you're going to cut one of the ends off to connect it to the batteries. The other end has to connect to your power supply on your computer, which is a male end.
Yeah.
So you want the female to the male so you can connect it to the female end, so on the cable, so you can run it directly into your battery array, which is totally awesome. Just make sure that it's the proper gauge. Yeah, if it's that thin, don't do it. It don't work well. That's designed for like low-end servers at like 50% capacity, so like your really cheapo one use. You want to be about that thick, which is your actual power supply cable. So, come on. How do we solve this?
I cannot use all of them because you agreed to limit it to 1,000.
So we got to cut at least one of the cards out. All right. How many cards did we cut out?
You cannot use 3, so you have to use. Yeah, you can use. I mean, you're allowed to use 2.
You're allowed to use 2.
Not good solid.
Uh, 12,000 watts.
You have 12,000 watts, correct, per battery.
Divided by 3 people will give a 4,000 watts for one person, and that would give 1,000 for device plus 3,000 watts for graphic cards. So everyone can have 3,000 watts of graphic cards together. Is that right?
3,000 watts or 3,000 watts of graphics card.
Yeah, I mean, 3,000 divided by 280, which gives us about 10 graphic cards in each device. So every person can have 10 cards.
I mean, can you install 10 cards?
No. Well, actually, there is a new device you can. I don't know if y'all saw this or not, but it was, I think, an Asus board that has like 52 slots for graphics cards. It's a Bitcoin mining rig. Don't get excited. I promise, it's not that great. So, all right, let's look at this a different way. How do we break this down? Do we run this in series and parallel? Series, parallel? How are we going to run the batteries?
Well, it depends what your power supply accepts.
Depends on what our power supply accepts, and it depends on
12 volts or something around that.
12 volts.
Or 24 maybe.
So we got a 12 volt power supply. We got a 12 volt battery. Got 1,000 amps.
That should be parallel.
What are we not looking at? It's not in here, but we got to consider it.
We've
already got the information.
How many volts can we connect to each device?
How many volts can we connect to before we blow our computer up? Very important question. How many thinks we can put one battery? 2 batteries? 3 batteries?
Can
many
you
batteries?
combine it all? Because we don't have cables.
We don't have cables? We have cables. We've got the female to females, and we've got the cables to connect it to.
Can you do?
And what is the voltage for each device?
For each device?
Yeah, 110, 220.
Yeah, we'll say 110.
Ah. Okay.
So then 16, we have to. Okay.
But it's AC. Is there like?
So
AC?
16 batteries, if we do it in order and subsequent, it will give us 192 volts. So I guess we will not connect them in parallel.
We'll not
Because
connect them in
if we
parallel.
connect them in parallel, that would give a very high amperes for all the batteries.
It would
We
blow
have
up
to
your
lower
system.
the amperage.
Yeah, you have to lower the amperage. Now, here's something really cool about devices. So, a lot of the devices that we have, like our iPhones, our Androids, especially the Samsung devices, are designed to perform in the 110 to 240 volts range because they're designed to work in both the US and Europe, who have totally different power standards. So when you look at your walls and you got those little, really annoying, really weird connectors, it says 250 volts on the back at 10/16 amps. So that's a conversion between 110 and the 240 range. So 220 to 250. So just so you know ahead of time. So let's go ahead and check this out. Oh wait, where's the answer? The answer's not here. Huh. Yeah, so it's 3 batteries. Yeah, it's 3 batteries. Now, you want to run those in, like you said, series. So that gives you the lifespan of the battery base, which is amperes, which we already have, which is 20 hours. So each person gets 3 batteries, up to 4, to the extent that if you do it in series, and you've got up to 24 hours to play on. And that's because of the draw, because the calculation you have to consider is also the decrease based on the high amount of pull on the device, which computers are power-hungry monsters. They just your electric bill just goes sky high. I can't even imagine what a battery would happen if it was a Bitcoin miner. It would just blow up. It'll be awesome. I'll try it sometime. So horsepower. Now we're getting into motors. So this is where it starts to get important to us if we're going to build something that can move, because you got to have some kind of a motor. Now the horsepower is broken into, like I said, the ability to move stuff. It's broken into what's called foot-pounds. So 1 horsepower is the ability to raise 330 pounds of coal 100 feet in 1 minute, 33 pounds in 1,000 feet in 1 minute, or any other combination of feet and pounds as long as it equals 33,000. So this is the magic number. It's 33,000. No matter what combination I do, the math has to come out to 33,000 in 1 minute. So it's the ability to measure, the ability to move weight over distance in a specific period of time, which is calculated in 60 seconds. Now, base horsepower, or BHP, is horsepower per ton, not to be mistaken with ton, US ton, but the metric ton, which is a distinctive difference in weight, 2,204.623 and 2,000 pounds, which doesn't sound like a lot until you start looking at something like, I don't know, a bulldozer. Then, 2,000, 3,000, 4,000 horsepower motor, you're missing a lot of extra weight and extra performance that you could have otherwise gotten. Now, this is breaking it down. 1 horsepower is equal to 746 watts, or 550 foot-pounds a second, which this is the normal metric that most mechanic shops like to use if they're getting into the engineering portion, which is foot-pounds per second. These are all the applied usages of the formulas, depending again on purpose. You could have a lot of different utilizations. If you're looking for a generator, for instance, for your house to keep everything running, you want to use the watt-based application. If you want to drive your car, you want the horsepower application because you want to move stuff. You don't just want power You want raw power for moving objects and not for generating energy. Now, thrust is where things get really complicated. There is a large number of things that impact thrust. Air pressure, temperature, ambient operating temperature, pitch of the blades, whether you're using a propeller-based system, whether you're using some kind of propulsion-based system, whether it's ion propulsion or rocket-based fuels or some kind of oxidizer like NASA likes to use. It all really depends, and different applications have different generations of force measured in newtons, lbf. So we'll get into that in a minute. So it's measured in pounds of thrust in the US and newtons literally everywhere else. We're just the ugly duckling in all things, including measurements for the metric system. And 4.45 newtons is equal to 1 pound of thrust. So the pound of thrust is how much it takes to keep one pound object, so one pound object unmoving against the force of gravity. And this translates to the 4.45 or the 1 for keeping that 1 pound against that gravity for 1 second. Now, the acceleration is very important. Acceleration is very important because Earth's acceleration is not the same as the moon or space, or if you're in some kind of weird magnetic field. It impacts gravity, which drastically alters how much force you need. The reason why this is important is, say for instance you're trying to build the Mars rover. What you don't want to do is calculate it based off of Earth's gravity and you just launch some $15 million device into oblivion because you gave it way too much kick. It's kind of like letting me have the salsa. I'm just going to drown it. So that translates to, feet per second per second. This looks like a typo. It's not. It's really confusing. So this is 32 feet per second. It's moving 32 feet in 1 second per second. So every second it's moving 32 feet per second, or 21 miles per hour per second. So that's why I put that one in there. It's a lot easier to understand. And the per second thing confuses a lot of people. So the idea of applied thrust is you throw 1 baseball per second away from you at 21 miles per hour. Your baseball would generate the equivalent of 1 pound of thrust. And you'd also have one really short NBL career because that's terrible. The average pitcher generates between 91 and 100 plus miles an hour throw. So the amount of force they generate is actually the reason why they're so dangerous. They can actually kill you. So it's pretty cool. So as I said before, there's a lot of things that can impact thrust. Power to weight ratio is what's going to be most important to you guys, and the newtons lbf. So when you're looking at an engine, a thing a lot of people don't realize is engines are heavy. Engines are what make you move, but the weight of the engine also comes at a cost because the power to weight ratio, sure, it went from 0 to whatever, but you also added 600, 800, 1,200, 2,000 pounds for this motor. It's the reason why when you look at places like NASCAR, they've ripped out the current motor, as great as it might be, and replaced it with a titanium motor that's exactly the same. Because the motor's got a higher level of durability, can handle a lot more heat, and weighs substantially less, which drastically shifts the power to weight ratio, which is why their cars are just unbelievably fast. Now, if you really want to have a field day, take out the NASCAR motor and put it on a lawnmower. You're really going to have a good time if you don't, die when you're moving 900 miles an hour, which is what those drag cars effectively are. It's pretty much polycarbon or some kind of just flex carbon, literally sitting on like this tiny, effectively go-kart frame, and it's got a jet engine attached to it, and they just go 1,000 miles an hour for like 2 seconds because the fuel's gone. Now, other major considerations is air pressure, temperature, drag, and gravitational forces. Can anyone tell me why air pressure is important?
Because if you go over some speed limit, the air pressure is Q. So the resistance of the air is power of 3.
Correct. So when you're starting looking at something like a helicopter, the reason why helicopters can't go above certain heights is the air pressure changes too much to the point to where they can no longer generate adequate lift, and they can literally hit a point where they just simply can't go any higher, because their engines are designed for a maximum power to weight ratio, and it generates excess thrust, which decreases in terms of excess thrust as they go higher and higher and higher, to the equivalence to where they eventually reach a 1-to-1 ratio, which means they're no longer gaining height, they're literally just maintaining that location.
So it can go high because of power and engine
It's,
power.
Because
it's
of
not
density
just
of the
power,
air.
it's air density. Because the air gets thinner and thinner the higher you go. It also gets colder, which does help some, but the offset between that and the pressure is just non-comparable. But the other issue with that, and the reason why helicopter pilots have to be careful, is if they go too high and they clear that threshold and they're up at the absolute 1-to-1 ratio and the wind blows, it changes the air pressure. And all of a sudden where you were at a 1-to-1, you may go up or you may go drastically down. And the issue is if you're a 6-ton object and all of a sudden you were just dropped 12 feet, well, you're not exactly going to recover as quickly. And if you're near a mountain, for instance, which is where this normally happens, so if you're going and you're trying to climb Mount St. Helen and you go above a certain level, they cannot come save you. And that's why the Sherpas are so important, and that's what they do, is the Sherpas will go up beyond the points to where the helicopters can, and they'll carry you down to an evac point, which is a safe distance for the helicopters to fly in, and they can't fly above that by regulations because otherwise it'll kill the helicopter pilots or at least make them crash, and now you got to go save 2 teams. So, when you're looking at aircraft, excess thrust is the primary force because you don't have to worry about air pressure if you're a rocket engine. You just have to worry about how much sheer raw power can I generate and just launch myself into oblivion at an astronomical level of speed. Now the issue is fuel consumption. The faster you go, the more fuel you need. That's why rocket ships, for instance, from NASA, consume millions of gallons of fuel to get one aircraft into space. And that's because their power to weight ratio, they have astronomical amounts of power, but the thing weighs 65,000 pounds by itself for just a cargo bay item. And then you start looking at the actual craft weight, the container weights for the fuel itself weighs weight, which is the other things you have to consider is what is the weight of the fuel I'm going to put in the craft to fly it, which is something a lot of gas-powered RC builders forget to consider, is that fuel actually carries weight. And when you put something that's about 8 to 10 pounds per gallon with a 10-gallon tank, you just added 80 more pounds, which could pretty much make your craft a 1-to-1 ratio or even less, and it can't even lift off, which is generally what happens, and they end up doing half tanks and they end up losing races all the time. So, for maritime craft, so you're looking at stuff like ships, like aircraft carriers, your average boat in your backyard. They're mostly leveraging pistons, so they're using combustion-based, and the power to propellers is where the primary indicator will come from. That is just like with cars, they call it wheelbase horsepower. It's not how much power your engine can generate, but how much power I can get to the wheels. Propellers are the same for boats. How much power, sheer raw horsepower, can I get to the propeller itself to propel me forward? Now, this is getting into ohms, which is the SI unit for resistance. Ohms are cited a lot for a calculation basis for normally the peer base, so it's power, current, voltage, ohms. Ohms, the most that you'll probably need to know about ohms is calculating the capacitance and calculating the resistance so that you can actually do that. And I actually include this really nice chart to help you do that. So the last band is always the multiplier. A lot of people get confused because there's 4-band, 5-band, 6-band. I've seen 15-band resistors. You're looking at things that are in medical devices to where if it's even a micron of a voltage off, someone's going to die. And that's because you've electrocuted their heart, you've destabilized it, and it's in pacemakers, and they're just dead because any arrhythmia whatsoever could kill them. So the first digit and the second digit and the third digit, if it's a 4 or a 5, the fourth, they're all multiplied together. So you multiply these, and then you get your numbers. You multiply it, calculate your tolerance, and your temperature coefficient. Now, if you notice here, it's in ppm, so that's parts per million. So that's also leveraged in water. I've never really had to worry about temperature coefficients and resistors, mostly because I take a lot of care to ensure my electronics run at a cool ambient temperature, and I use proper cooling, so I've never had resistors cook off. But the reason why this is relevant in the temperature coefficient is you can actually overheat your resistors and blow them. And if you blow the resistor, you blow the circuit. And the issue with that is if you blow the circuit, if you've damaged the circuit connectors, you have to resolder that, or you, most motherboard instances, if you don't have proper cooling in your computers because of this, your resistor explodes it up because of overheating, and your computer is just dead because the vendor's not going to go out of their way to resolder a resistor on. They just don't do that because they don't care. Now, again, the other thing you have to keep in mind is plus or minus 5% or plus or minus 1%. In certain instances of assets, you want an incredibly low tolerance. You don't want any fluctuation whatsoever. So high-end electronics, you're going to see a violet band. So if you see blue, purple, or green, you have an incredibly sophisticated, extremely intolerant device. These are devices you absolutely do not want to mess up on your voltage because they are using a lot of care to ensure there is no fluctuation whatsoever. Your computer components normally have these for high-end gaming boards. And that's to control to great detail the amount of power the board or component's getting at any given time. Air traffic controlling devices normally will use a higher end resistor, and that's to control the device's ability to receive power, send power. So your wireless controllers for your RC cars or drones, for instance, they're going to use the higher end resistors. So when you start looking at silver and gold ones, it's a device that's like, yeah, I don't care, just give me power, just don't kill me.
And VPN shows how much the deviation is, or what? I mean, or no?
Honestly, I don't know. I couldn't tell you that.
I mean,
again,
other in types of resistors that vary because the temperature goes up and the deviation of the resistance goes up.
like I said, I couldn't tell you. I've never had an issue where I had to worry about it. But that's because, again, I worry a lot about ambient temperature. So like for me, for instance, if I have any concerns for cooling, I use a liquid cooling device. And so it fixes all of my problems. I don't really have that issue. If I have, for instance, I'm working with a rocket-based item, like a rocket engine, I'm building into some kind of model, I'll put vacuums inside it with a liquid nitrogen cooler. So I'm going to drop the temperature to an extreme low, and it's not going to matter anyways. Negative pressure. If you're going to put something that sucks in a lot of air, like a rocket, into like, a car, I would highly advise that you cut slits on the sides for vacuums because you will shatter your windows. And it's pretty awesome. So just keep that in mind. There's some pretty great YouTube videos of people forgetting that. Now, getting your cabling. This is where most fires happen, is with the cabling. So cabling gets incredibly hot incredibly quickly if you use the wrong gauge. So it's very, very important that you understand what kind of gauges you're using. So most of these you guys are probably never going to see except in your houses. So your 15, your 20s, and your 30s, these are the lower gauge. You've got 16, 18, 24 gauge. 24 to 18 is realistically what you're going to work with on a regular basis. If you're working with incredibly small electronics, you might go into 26s or 28s. But for larger places like commercial buildings, they're using these. AC units, fridge, washing machine. It really depends. But again, it's incredibly important because if these cables overheat, which they will, it will start a fire. Because what will end up happening is it will melt off your shielding that you see here, and then it will keep getting hot, and any material that it makes contact with, like the wood in your walls or your drywall, it'll eventually ignite it. And a lot of house fires are caused by that. Now this here is a multimeter, and you use multimeters to test AC and DC power. So you're going to have to get one of these if you're going to actually build something. They're incredibly cheap, like $3 US, and that's in the US. I doubt that they're more than like $1 here because you're close to China where they all come from. So yeah, like multimeters in the US are so expensive for literally no reason. So these are going into the charts, like I said. I've included a lot of these to help with the math because there's just an astronomical amount of math. That's what most of it is figuring out the watts that you're going to need, the weight, power to weight ratios, what kind of motor you're going to have, calculating based on what the amount of force that it can generate, which you can't calculate until you've built everything else out. And then you have to figure out, well, what kind of thrust do I need? What kind of force do I need to generate? Is it propeller? Is it going to be rocket fuel? Well, how much weight do I have to play with? If I've got more weight to play with, I use rockets because it's cool and goes fast. Or if I don't have a lot of weight to play with, I'll use a propeller. And I'll never clear Mach 1, which makes me really sad. Because I don't know if you've ever seen this, but drones with a rocket engine go like 400 plus miles an hour. And it's like, wow. And it's just, yeah. Talk about just terrifying your neighbors. That make you mad. But yeah, so this is going into all the measurement units. And like I said, I'm going to give you guys a copy of these slides. This chart is the very useful chart to figure out when you see something weird like voltmeter or a Tesla. I've never seen, honestly, any of these except for the second meter. Now, this is the only formula that's actually useful off this entire chart, but this formula is so awesome that I included the entire chart. So this is actually giving you the electrical motor formulas for the efficiency. So efficiency is incredibly important because the amount of power that you're cranking into it versus what you're getting out of it, that's very important to almost everything you're going to use it for, whether it's an RC car or a drone or an RC submarine. You can build a lot of really cool stuff, by the way. This is incredibly important because the more energy you waste trying to get power to a device like a propeller or another propeller like a spinning propeller for a lift or a propeller for a craft or wheelbase, the more power you waste, the more energy you waste and the less efficient the motor is. Which is why if you can get an extremely high efficiency electric motor, which is the ideal one to get, if you have issues with like energy capacitance, for instance. So just a rule of thumb, most gas-powered motors are 60% efficient. Most electrical motors are 95% efficient. So it is a substantial difference in performance efficiencies. The catch-22 is gas is extremely readily available. Good luck finding a Tesla charger. So now, this is going to break into practical projects of things you can build with the knowledge that's inside this slideshow. You can build drones, remote-controlled devices, IoT devices. You can build forges, smelters, reactors, colliders, assembly lines, production lines. You can build a starship, a mobile command center. These are actually my current projects, which are totally badass, like hardcore. Definitely the hardest projects I've ever worked on, which is why, like I said, unless you're using auxiliary source power, that's why, because, you know, I'm a huge Trekkie, and I was like, auxiliary power for life support, so I don't die in space. Yeah, that's a thing, because I'm actually trying to get into space, or at least close enough to where oxygen isn't in the air anymore, really, so, you know, air stops working, I kind of die midair. And it's just going to run for a few hours and then, yeah, bad news. But yeah, you can build a lot of really cool stuff. My favorite one, though, is the smelter and the reactor. Because you can build a nuclear reactor with just this information I've given you. And a vacuum space and the right components to create the vacuum tube. Plasma and some tungsten rings, absolutely. Nuclear reactor, totally cool. Salt water, electrolysis to strip it out to deuterium. Inject the deuterium in. You've literally got a functional reactor. It's like 150 million Fahrenheit. Really cool. Oh, sorry, Kelvin. I'm so used to Fahrenheit. But yeah, the forge, if you've got like a lot of aluminum cans laying around, chop them all up. I found that the easiest way is to get a grinder and literally you just take the can, you crush it by stomping on it, and then you pull it back apart and it weakens it. You throw it in, it just grinds it to pieces. Then you take those pieces, throw it into just like a generic forge. You melt it down, turns it to liquid form, pour it into ingot form to store it for long term, and you can literally just melt it down at any time and just pour it into plating, for instance, creating negatives with clay. Incredibly easy, especially if you have artistic friends. Yeah, they can make you a lot of really cool negatives, and you can make plating for your aircraft, or you can make side body parts. And the best part is you can just heat it up with a blowtorch real quick, and it'll fuse together. And you can literally make entire RC bodies, like hardcore. It's really cool. You can have a lot of fun with it. So, a couple of forewarnings. This has been me sometimes, where I just get totally obsessed. You will get so obsessed, you just have to finish the project because it's like, it looks amazing. I've just got to get the battery right. And you just end up turning into this monster. Like, it's just, you smell bad and you look like you've just been put through like a meat grinder. It's just terrible. Like, hardcore. Take a break, take a breather. I found that the best thing to do is if it's just not working right, just step away for a little while. And when you're doing pretty much anything else, especially trying to sleep, you realize what the problem is, and now you gotta go get up and go fix it. The other thing is financial costs. You're gonna build something simple. You're gonna love it. It's gonna be awesome. Then you're gonna wanna build something even cooler. Then you're gonna build a forge. Then you're gonna build a smelter. Then you're gonna build some kind of crazy assembly system for grinding up wood chips to generate power from a gasifier. And you're playing with transesterification and pyrolysis. Then all of a sudden you've got a manufacturing facility in your backyard where you're making your own custom jet fuel, and your neighbors are pissed because you're making jet fuel in your backyard. Might be speaking from experience there. But yeah, really cool. You're gonna get sucked in. Stainless steel is extremely expensive in the US. It's probably dirt cheap here. I've literally seen issues where I found like chippers and grinders and pellet millers here for like 50 US, and the shipping was like 1,500 US to get it sent to me. So you guys are really lucky in that regard, because pretty much anything manufacturing related is made in China or Korea. One of my favorite photos and favorite sayings: just because you can does not mean you should. This is an actual photo from, you guessed it, a cobra, where this woman kisses the cobra. Why? I don't know. I've done a lot of things where my friends are just like, dude, what are you doing? Like, nuclear reactor in my backyard. And they're just like, are you serious? And I'm like, yeah, check it out. It's radioactive. Like, I'm melting palladium into cadmium so I can make my own batteries. And he's like, dude, you're insane. I'm like, yeah, it's a radioactive battery, but it still works. Yeah, kiss the cobra. Yeah, don't do that. I mean, if you've got to look back and say, dude, this is awesome, but dude, and your friend's like, dude, that's insane, you might want to reconsider your next couple of builds, because you're going to use that build for something else.
Change friends.
Just like I did. Yeah, change friends. Yeah, I like this guy. We're going to be friends. Absolutely. So that's about it. Now, what's the time?
6 minutes.
You have 20 minutes.
20 minutes?
Right?
Oh. Total?
It's 20 minutes now and 20 minutes you have.
Oh, so I've got 40 minutes.
Yeah.
Okay, good. All right. So,
No, you have
20
20
minutes.
minutes.
I have-
For the end.
what? Oh, for the end of the workshop.
Yeah.
Yes? Okay. All right.
Questions?
We'll do questions. Okay, we'll do questions, and if you guys want to build something, I've got everything you need to do that.
I got a question.
Go
If
for
you-
it.
At home, when you put the wires for your sockets, you showed us the table, which is 2.5 millimeters is
Yeah.
15 amperes. And is it common practice to put some substance as a heat dissolver, because the wires inside the wall, they give heat? So if it is empty space inside, or maybe something around, cement, so does it make sense?
Generally, no, and the reason why I say that is again, for instance, if you're going to use 20 amps, you got a 20 amp circuit, you don't want to use a 20 amp circuit with a 20 amp wire. You want to use a slightly higher gauge, and that way you can't overheat the wire. You can't even run it at 100% load. And again, it comes back to good engineering practices. Will you spend a little bit more money? Absolutely. But at the same time, if you want to upgrade, for instance, from a 20 amp to a 30 amp, so like you're running 30 amp like an average DC does for data centers, you can just go in and simply switch out the 20 to the 30 with no concern about overheating the wall, because even if you could run at 30, which you probably won't, you can still upgrade to it with no concern. Whereas if you went from a 20 to a 30, you'd have to rerun the entire wire. And so that means you have to rip out the drywall, pull everything out, unpack your heat resistance material, pull everything out, insulation out, which is a nightmare, and it itches like crazy. Run it all out, run it all back in. Then you have to pay a master electrician in the US to come and plug it in, even though you can run the entire thing yourself, because you're not a master electrician. So Yeah, it's generally a nightmare. But yeah, the other piece is if you're running a full load on a full 20 amp on a 20 amp, you shouldn't have put it in a 20 amp. You should have put it in a 1240, and that way you're not running at max load. Because again, it's never safe to run anything above an 80% threshold, which is why that 20% is always there, and that's for safety reasons or surges. So say for instance you've got 7 servers plugged in, and all of a sudden you just reboot them all of a sudden because you ran a command by accident. Well, if they all spin back up and there's not the extra bandwidth, it's just going to kick the breaker, and you're in for a bad day. And manual power cycling, which is great if you're in your office bedroom, it's not so great if you're 500 miles away. So hopefully you got smart hands, and that's 150 US an hour. So next question.
Just like considerations that like money is not the only matter. If you use drones, you also care about the weight. So
Yes.
there may be a reason why you want the battery to discharge 100%, so you don't have to put another battery in it.
Well, that's where you would go and add a second battery in series or parallel based on what you need. For you, it would be parallel, so you have the extra battery life. Now, the other... Go ahead.
It may be better for me to just replace it more often because it will reduce the weight of the drone.
Well, lithium-ion batteries don't weigh that much, so the first concern would be if you've got the extra battery and it's weighing it down to the point where performance is dropping substantially, you might want to reconsider either your power-to-weight ratio or something else.
They're kind of heavy for
Is there any difference between 100% battery and zero battery? Like,
Well, oh, so you mean fully charged
in weight,
and
charged,
completely
yeah,
empty?
In weight. Is there any difference?
No, there's no measurable difference. No. Not unless it's a chemical battery, in which there would be a barely noticeable difference. But yeah, like a regular lithium ion, you're not going to tell the difference.
It's pretty hard to find lightweight laptops because they will have very small battery life.
Yeah, and that's generally one of the issues, but at the same time, because it's a smaller device, it has less power draw. For instance, I've got 2 laptops here. They're both XPS's series, but one's got a 45 watt and one's got a 120 watt. But that's because of the power difference both in draw and in charge rate. So this laptop can literally run for days. That one can run for about a day. But that's what it's designed for. It's designed to be extremely lightweight, whereas this one's designed to be a workhorse. So.
Any questions?
Can you tell, just some time, so one of your most dangerous experiments? With
Oh
the
God, yeah, definitely a nuclear reactor. Yeah, that was just like, so I'm working on a project called Power Core, and the idea is to completely eliminate the use of fuel-based rocket systems, so that I can launch something with something that is designed to be more than just a one-shot wonder, which is what rocket ships are. They're awesome. Don't get me wrong. The things NASA build is just mind-shattering. Like these things are entering or exiting atmosphere thousands of degrees. Like it's just insane. These things are amazing pieces of engineering. But the issue is the cost. So to put a rocket in space, it costs $4 million in fuel, just in fuel, to put it in space. Power Core eliminates that cost entirely, and it drastically increases the power-to-weight ratio, because my current Power Core weighs less than 2 pounds. The average rocket for one rocket weighs roughly, if I'm not mistaken, like 80,000 pounds. So the power-to-weight ratio times 2, plus the other containers and the other rocket fuel, is just insane amount of extra weight. And so generating the extra power is what's allowing me to do that, while also reducing the weight and the extra capacities. So that's why I'm really interested in the project, because if it actually works and I get all the components that I need and I can finally get the permits, which is why I'm looking to leave the US, come here, because Ukraine is like, hey, you want to try something? Yeah. So the Ukraine's amazing, by the way. This country is just outstanding when it comes to R&D. You guys are just totally tolerant within safety reasons. I've already gotten that talk. Make sure you're safe. But it's not like the U.S. where it's literally you have to have like 4 permits to have a cow sitting in your backyard. It's just crushing. I mean, I've been waiting for 4 years for permits, and I still haven't gotten them in the U.S., which is why I'm leaving. I'm just tired of it. I mean, I talked to Canada, and they said they'd give me the permits in a day. So, hoping the Ukraine's just like, hey, come on up, have some fun. But yeah, definitely the reactor. I mean, that thing is spitting out radioactive material. I can literally like take silver and just sit it there, and then like walk away for a little while and come back and literally just take it and then set it down for about 28 seconds, and it melts into cadmium. And then I can literally just scrape that into a bucket, melt down some nickel, blend it together, and I've got a nickel cadmium battery. It's awesome. And extremely dangerous.
And do you have any portals?
No, God, no. That is extremely. Is that recording? Yeah.
It's like,
Too late now. Yeah, it's no way. Like it's technically they're legal, but the EPA gets involved, and they're like, we got to come inspect it, and then the county gets involved. It's like, why do you have a reactor in your backyard? And then it's just like too much trouble. So
What your
it's-
neighbors say.
yeah, it's pretty awesome. But yeah, they're not as dangerous as you might think, especially if you're not messing with uranium or plutonium, which, by the way, you can totally YouTube and figure out how to make yellow cake uranium in your backyard. It's pretty awesome. That's another project not in the United States because that's highly difficult. But yeah, I'm looking to make some uranium just for fun. But I need the uranium metal core for experiments. I want to see how NASA's powering the long distance satellites. They're using uranium cores or plutonium cores. I can't remember which. But yeah, it's non-weaponized anyway, so it doesn't matter. It's a fuel-based rod. But it's designed to last like forever. And that's how they're able to get way out to like Saturn and Jupiter and take all these crazy pictures and come all the way back. Plus, thousands and thousands of pages of physics that are just mind-crippling.
So with this reactor in your backyard, can you just use it to power up your house?
Mine's a DT reactor, so mine's not designed for power generation. Mine's designed for production of tritium. So I use a lot of tritium in my experiments, and so I need a tritium. I could care less about the power or the neutrons. They just happen to have a use, so they're there. But no, I really don't care about power. But you could. You totally could, because it does release energy on every reaction.
Endlessly mine Bitcoin?
I mean, I guess. I don't know. I'd have to actually, that's a good question. How much power is produced? Let me look into that.
Oh, yeah.
How much it would cost for the Chinese
Well, a couple
or
grand.
Ukraine?
And build it. I mean, a couple grand in the US. So, I mean, hey, China's like right next. I mean, we could build a few. We could find out.
It could be a project in Ukraine.
Absolutely. That's the idea. One of the projects I'm looking into is moving one of my power generation projects here, and then sucking in all the Bitcoin miners for another project of mine. And I need the asset value of everything that they've got, not so much the coins themselves, but from the project. But yeah. Any other questions?
What do you think about the catapult into space?
Catapult wouldn't react as well as you might think because it arcs, but a railgun would. If the device could survive the exit.
Yeah.
But yeah, you'd have to have someone crazy enough to get shot out of a railgun.
What is rail?
All right, the whiteboard. Okay, so the easiest way to understand a railgun is you have a long strip of magnets that are increasingly widening, just barely. And then you electrically charge the magnets. And the more power you push in, the more expelling power they have outward. And what you do is you put something in the middle of it, launch it perfectly through the middle so it doesn't collide with either side. The magnetic fields will balance it out, and it launches it really, really fast. So the military, of course, US being who they are, turned it into a gigantic killing weapon that can obliterate the entire countryside. Which, of course, they were going to make it into a gun and not anything remotely cool or useful. But yeah, they put it on an aircraft carrier and they tested it once and blew up an entire mountain. So it's safe to say it would vaporize an entire city just traveling through it because you don't have a structure hard enough to stop the round, which is literally just a chunk of metal that they just launch at stupid high speeds and it just obliterates everything. The vacuum left behind is just, there's no way they could ever fire it at anything without violating all the human emissions and all the other rules, like just bad news bears. But yeah, it's really cool.
If you use the railgun and you want to launch electronics somewhere, wouldn't it like cripple the electronics because of magnetic field?
Yeah, unless you generated an opposing magnetic field to repel the magnetic field. So magnetic fields that are a matching pair repel each other. And so the idea is to generate a magnetic field with the magnetic fields that are matching paramagnetic fields, which repels the object. And so you'd have to just have the ability to generate more electricity inside than you would outside. And that's the current problem, is figuring that out, which is where I'm hoping the power core comes in. Because if that actually does work, then you could use a railgun to launch something into space, which would be really cool. And I'm going to name it the Shepherd's Gate. Because Stargate's my favorite show. Yeah. But yeah, pretty cool stuff. Any other questions? No?
Thank you.